Very well. So I got some new markers today. Now, let's see what we have. So far we talked about line integrals. Now we're going to go over more examples, then a quick introduction to conservative vector fields. Objective. Vector field. And the line integrals when we're dealing with vector fields. Well, what we learned so far, recall that. We said that we have nice vectors in two-dimensional space and three-dimensional space. So suppose you have V equals to vector A comma B. We can generalize the idea, and instead of having a vector with two scalar or numbers, we can define functions, vector functions with graphs that have a lot of vectors in them, and we call it a vector field. This is just a vector in the plane. So we take a function, bolded f of x comma y, and we define a vector. That vector depends on functions like f of x and y and g of x and y. So for each different x and y values, different positions in x and y plane, you get different vectors as the outcome. So if you want to think about the range of this function, the range is a collection of vectors. So the graph of this function is not a continuous or discontinuous graph that you saw before. It's going to be a bunch of vectors in xy plane. So here you have x axis, y axis, and then you keep having these little vectors in the space. It might behave like this. We dealt with a lot of vector functions last time. You might see some pattern. You might see no pattern. Remember that we talked about the wind, the direction that wind is moving related to hurricane. We have gravitational vector field. We also have magnetic vector field. So depending on the branch of science that you're working with, you're going to work with different vector fields. We also said that, hey, we can define a vector in the space, like vector u, with components A, B, and C in the space. And then, as usual, we can generalize the idea and define a function, a vector function in the space. So the vector function in the space, f of x, y, and z is equal to, so this function, for each position, the outcome is a vector. So it has p x, y, z, q, x, y, z, and r of x, y, z. R of x, y, z. These are the components of this vector function. In the space, you have a collection of vectors as the range of this function. Well, then we start talking about defining an integral over a curve. Line integral. Line integral. So we say that, hey, suppose you have the integral of a function like f of x and y over curve C. And then to find this integral with respect to the length of the curve, we remember that we need to get rid of one of these variables because you only have one integral. Later on, we're going to talk about how to convert the line integral into double integral or vice versa. But for now, if you have a line integral of function f of x and y over curve C with respect to the length of the curve, we need to get rid of one of the variables. Depending on how C is defined, we can find a relation between x and y or x, y with a third variable. Very well. Let us go over more examples to feel more comfortable about how to deal with these types of integrals. Then we're going to introduce a new formula, how to use line integrals when it comes to vector fields. Example. This example says, well, evaluate the line integral of function y times sine z ds with respect to the length of the curve. The curve is defined this way. Well, C is the circular helix. Given by equation, x equals to, well, cosine t, y equals to sine t, and z is equal to t, while t is bounded between 0 to 2 pi. So we want to calculate this line integral. As you can see, you only have one integral and you have excess variables. It means that we have to get rid of one of these variables somehow so you're able to calculate this line integral. Very well. So you might say that I already know y is equal to sine of t. So I can substitute that here. Z is equal to t, I can substitute it here. And I already know that t is bounded between 0 and 2 pi. What's left? ds is left. So step by step, we try to convert everything and write it in terms of t. So note that. We already know that y is equal to sine t and z is equal to t. So integral becomes the integral of, well, sine t times sine t, and now ds. You need to calculate ds. And t is bounded between 0 to 2 pi. 0 to 2 pi. What was the formula for ds? We know that. We also know that ds is equal to square root of, well, the partial derivative of x with respect to t squared plus partial derivative of I with respect to t squared plus partial derivative of z with respect to t squared dt. Now let us calculate this guy. ds is equal to square root of, well, partial derivative of x with respect to t is negative sine t squared plus partial derivative of y with respect to t is cosine squared plus partial derivative of z with respect to t is just 1 squared. So ds is equal to square root of 1 plus 1, which is square root of 2. So we have everything that we need. So the integral becomes the integral 0 to 2 pi sine squared t times square root of 2 dt. So sine squared t, we need to convert that. Sine squared t is 1 minus cosine 2t divided by 2. We can write this square root outside the integral. And here we get t divided by 2 minus sine 2t divided by 4. Well, t is bounded between 0 to 2 pi. If you plug in 0 or 2 pi, this guy is always 0. So we get square root of 2 times 2 pi over 2, or square root of 2 times pi. Very well. So far we learned that if we have a line integral for a scalar function, we just need to get rid of excess variables. From scalar functions into vector functions. Now we are ready to discuss the integral of vector functions. So far, we introduced the line integral of a scalar function. Like integral of f of x, y, z ds over curve C, smooth curve C. Remember that. Recall that. A vector function is defined this way. F of bolded f of x, y, z is defined as, for example, the first component is f of x, y, z. The second component is g of x, y, z. And the third component is h of x, y, z. It includes some scalar functions. Well, now how do we take the line integral of just this function? We are not focusing on the components like before. We are just saying that, hey, now that I have a vector function, how do you calculate the line integral? So let's take a look at this definition. Let me write the definition here for you. Then I'm going to write down one example on top of it. Let f, bolded f, be a vector function. It is defined on a smooth curve like C. This curve, C, is defined by a vector function like R of T. Your T is bounded between A and B. Then the line integral, of f of T dot, guys, note that this is a dot product, dot R of T over curve C, just write down dr, is defined as, well, f of RT. So we do the substitution, f of RT times R prime of T dt as T moves from A to B. Just note that here we have f of T dot dr. There's a dot product between these two vectors. This is your first vector, and this is your second vector. We can define a dot product between two vectors, and the line integral of your vector field dot dr is equal to the line integral of f of RT. We do the substitution. We take the derivative of our curve and we find the integral with respect to T. Our T is bounded between A to B. So there is another dot here. So let me just specify this. Dot product. Dot. We have two vectors and we get two more vectors, dot product between them. So give us an example. Sure, let's go over one example together. So note that here we have a vector field. We're going to introduce a curve which is defined in vector format. And again, note that here we have a dot product. Don't miss out the dot product. Otherwise, how do you connect two vectors and take the integral? Well, in this example, it says find the work done. Find the work done by the force field. Well, another example of a vector field, force field, which is defined to us as f of x and y equals to the very first component is x squared, and the second component is negative xy, or another representation is just a vector, so x squared in the direction of x-axis, and the second function in the direction of y-axis. So this is your force field. In moving a particle, along the quarter circle, which is given to us as, well, here you have RT. This is your vector, cosine T, sine T, and since it's a quarter circle, T is bounded with 0 and pi over 2. So remember that we're going to use the definition that we have. This is our vector field, and this is the vector representing the quarter circle. So the formula says, hey, the line integral of this vector field, f of t dot dr, or the work done along this curve, is equal to, well, here we have to substitute RT into our function and find the derivative of R and take the integral with respect to t. We already know t is bounded between 0 and pi over 2. So this is your x, and this guy is your y. Wherever you see x, you're going to substitute that with cosine t. Wherever you see y, you're going to substitute that with sine t. There you go. So we get x squared cosine squared t, comma, negative cosine t times sine t dot the derivative of RT. The derivative of cosine is negative sine. The derivative of sine is cosine dt. Now you have to find the dot product between these two. Well, remember that the dot product gives you the sum between the product of the first components and the product of the second components. This is what we remember from dot product. So if you have A, B dot C, D, the dot product between two vectors, you get AC plus BD. This is the dot product. So very well, this integral, work done, becomes integral 0 to pi over 2. The product between these two gives you cosine squared t times sine t. It has a negative sign in front of it. Well, minus cosine squared t times sine t dt. As you can see, you end up with one function in terms of t. Well, negative cosine squared, sine t, we get negative 2, integral 0 to pi over 2 cosine squared t. Sine t, you can use u sum. U is your cosine, and du is negative sine t dt. So this integral becomes 2 integral u squared du, or 2/3 u to the third cosine to the third power of t. T is bounded between 0 and pi over 2. If you plug in pi over 2, it's going to be 0. If you plug in 0, it's going to be 1. So you get negative 2/3. Very well. We say that a vector field is conservative if you can find a function that we call potential function, that your vector field is equal to the gradient of that scalar function or scalar potential function. So let us write this mathematically. And see what are we talking about here. Definition. A vector field. So we have a vector function like f, bolded f, capital F, is called conservative if and only if f is equal to the gradient of a scalar function. So this f is a vector function. This f is a scalar function. This is called conservative vector field, VF, vector field equals to the gradient of a scalar function, which we call the potential function. So this is your vector function. For example, let's give you one example. Let f, bolded f, be defined this way. You have your vector function 2xy plus z, comma, the second component is x squared, and the third component is x. Let f be a vector field. Question says, well, verify that f of x, y, and z, which is equal to x squared y plus xz, is the potential function for f. Okay, very well. So we have a vector field, which is f, capital F, bolded F. We need to check to see if this vector field is equal to the gradient of this function. We only need to check to see if f is equal to the gradient of f. So left-hand side is your vector field. Let's copy this guy down here. You have a vector, first component is 2xy plus z, second component is x squared, and the third component is x. Let's put a question mark here. We're trying to verify that. So let's put a question mark on top of it. On the right-hand side, you have the gradient of this scalar function, which is x squared y plus xz. But what is the gradient of a function? Recall that the gradient of a function is a vector function. Partial derivative of f with respect to x, comma, partial derivative of f with respect to y, comma, partial derivative of f with respect to z. So we have to do the calculation. We need to take the partial derivatives. The partial derivatives, the first component, partial derivative with respect to x is 2xy plus z. The second component, partial derivative of f with respect to y, which is x squared, partial derivative of f with respect to z, which is x. The first components are the same. The second components are the same, and also the third components are the same. So it means that this scalar function is the potential function for this vector field. So the answer is yes. We just verified that.